Hello, my name's John Evans. Welcome to this video on using TOPAS and jEdit to do a simple readfelt refinement. The things I'd like to go through in the video are on the screen here. As I say, I want to show you how to do a simple readfelt refinement in TOPAS using what's called launch mode. I want to give you a quick introduction to jEdit, which is an editor that we use to set up the input files to do this readfelt refinement. I want to stress that in this particular video, I'm just going to show you the mechanics of how to do things. We're not going to go into any of the theory of readfelt refinement or why things work. That'll be covered in later videos. I'm going to assume three things as we go through this video. I'm going to assume that you've already got TOPAS Academic or the commercial version of TOPAS installed. I'm going to assume that you've got jEdit set up on your computer already, and there's a video on how to do that if you've not done. And I'm going to assume that you've got a basic knowledge of readfelt refinement. So maybe you've used other readfelt software in the past, or you've read textbooks on the subject. So when we work with TOPAS and jEdit, the way that we work is summarized on the screen here. If you've used other readfelt software, you may be used to using a graphical user interface for interacting with the program. So what you do there is you click on certain icons or tick boxes on the screen to set up the instructions for the readfelt refinement. Now, TOPAS does have a graphical user interface, but for most things, I find it much quicker to use launch mode and set up all the instructions in what's called an input file. And that's the way that we're going to be working today. So what we're going to be using is using a free text editor called jEdit to make an input file. What an input file is it's a straightforward text file which contains instructions for the readfelt refinement. So for example, it could contain some general instructions about how to do the readfelt refinement. It might contain some instructions on the name of the data set that we're looking to analyze. And it might contain some information on the structures that are present, so the phases that are present in the data set that we're going to be using for readfelt refinement. So we're going to set up those input files in jEdit, and then what we're going to do is press a button TA with an arrow across. And what that will do is it will save the input file and it will tell TOPAS that's the file that we want to analyze. We're then going to switch to TOPAS itself to do the readfelt refinement, and then at the end of the readfelt refinement we'll be given a choice. If the refinement's gone well, we might want to save the results of that refinement into our input file. If it's not gone well, we might want to reject the results of that readfelt refinement and go back to our original input file. So what we'll do next is we'll switch to my desktop and we'll go through the process of performing a simple readfelt refinement using jEdit and TOPAS. Okay, so here we are on my desktop. What I've got is a folder here with two files into it, the data set that we want to analyze and a crystallographic information file which contains the basic starting information about the phase that the data were recorded on we're going to need for the readfelt refinement. I'll put a link in the comments below on where you can download those particular files. So let's look at them quickly. So the data set is a .xye file, and that's just a file with three columns. It's got the 2 theta value, the observed intensity, and the standard uncertainty on that intensity, XYE. And then the crystallographic information file contains information about the name of the compound, the unit cell parameters of the compound, the space group, and then at the bottom, the fractional atomic coordinates of the sites that are present in that material. So those are two straightforward text files. So to actually perform a readfelt refinement using jEdit and TOPAS, what I'll do first is I will launch jEdit. So jEdit should appear on my screen. You close this window. So this is what we should see when you start jEdit up. We've got a normal text editing window on the right here where we could just type things in. And on the left, we've got a series of menus. So to do a simple readfelt refinement in TOPAS, what we can do is follow the instructions which are in these TOPAS Durham menus. So if we expand those menus, what we can see is we've got a series of sub-menus set up for some of the things that you most commonly want to do in TOPAS. So there's a menu for a readfelt refinement, a Pauli refinement, time of flight readfelt, etc., etc. What we want to do today is a simple readfelt refinement. So if we expand that sub-menu, we get a series of new sub-menus. With each of these different processes, what we need to do is basically just start at the top of the sub-menus and click down each of them one by one, making some simple decisions about how we want to do our readfelt refinement. So the first one is select data file. So if I double click on that, I should get a dialog box pops up and it's already in the right directory, the directory that we're working in. And I need to select the data file. So here it is, y203 blah blah blah.xye. I click on open. The next menu is the instrument and corrections menu. I need to tell Topaz what type of instrument this was recorded on, and I'll come back to this in a second, but it was recorded on a diffractometer called the Durham D8, so I'll double click on that. The next thing I want to do, there's a choice here. I want to refine the 0 point used for the experiment. So the 0 point is, of course, if our diffractometer is perfectly aligned, then when we set the detector to 2 theta equals 0, it's in exactly the right place. It may be slightly offset, so there may be some kind of calibration on the 2 theta point of the detector that we need to refine. So I'll double click on that to refine a 0 point. Then I need some structural information. There's a folder here called structure CIF. We've got a CIF file for this example. So if I double click on read a CIF file, select that file, then it will be read into the input file. Okay, so at that point, what's been created on the right here is a simple text file with all of the instructions for doing a Rietveld refinement. So let's just run through that very quickly. The first thing is that any line that's got a little quotation mark at the beginning is a comment line. If you want to add a comment to your refinement, you can do that very easily. So I could put a little comment on that this is a demo refinement. Okay, so that's easy to do, and leaving comments is really useful because you can keep a record of what you've done. If you want to put in a bigger comment block, you can use the /*/ format. So if I type that in, okay, so anything between a /* and a / is treated as a comment by Topaz, and so you can put in big blocks of text if you want to leave a comment in your file. The next section of the file is the line here, the R factors to do with the refinement, how well the observed model and the calculated model fit will get written into this line in the input file. Next, we've got some general information about how the refinement is going to be done. So for example, this line here tells Topaz how many cycles of least squares to perform. It's set up by default to 100,000. We won't need anything like that. Let's just leave it doing 100 cycles of refinement, 100 iterations of least squares. We need to tell Topaz when to stop the refinement, when is it converged. So what we can do is we can use the chi-squared value, which is a measure of how well our model calculated pattern fits the experimental data. We can say to Topaz, when that number changes by less than this amount here, 0.001, consider the refinement finished, converged, and stop the refinement. Then the next information in the file, next section is some information on the data set used. So XDD is a keyword saying that some X-ray diffraction data information is following. So after the keyword, we've got the name of the data file that we want to analyze. The next line here, when we do a Rietveld refinement, what we need to do is we need to calculate the intensity at different values of 2 theta. And we need to tell Topaz what values of 2 theta to calculate at. And the default thing to do is to calculate the calculated data at the same 2 theta values as the experimental data. And that's what this line here says to Topaz. Calculate the model at the same 2 theta values that were observed experimentally. We normally want to fit a background function in Rietveld refinement, so we need to describe the intensity between the Bragg peaks. So this line here fits a 6th order polynomial function to the background. The next line describes peak asymmetry, so lots of peaks in powder diffraction patterns are asymmetric, and so this parameter called axial will describe the peak asymmetry. The next bit of information in the input file is about the diffractometer that was used. So this particular dataset is appropriate for a D8 diffractometer, which was set up with a germanium 111 monochromator at an angle of 27.26 degrees. Had a Vantek detector, and that setup gives me copper K alpha 1 radiation. So that's the information about the instrument, and from the LP factor, Topaz will know how to correct the model data to fit the experimental data. Here's the line for our 0 point, which we discussed a few seconds ago. Then the next section in the input file gives information about the structure. So the keyword here is SDR for structure. Here's the name of the phase, it's Y203. Here are the unit cell parameters A, B, and C. It's a cubic material. So what we would normally want to do in a Rietveld refinement is refine the unit cell parameters. So what I can do is I can put a parameter name in front of each of those parameters, LPA, and that will tell TOPAS I want to refine each of these numbers, but I want to keep A, B, and C the same. Here we've got the space group for this particular material, IA bar 3, it's a cubic material, body centered. Then the next lines tell us about the crystallographic sites that are present, the 3 crystallographically unique atoms, yttrium 1, yttrium 2, and oxygen 1, and their fractional atomic coordinates x, y, and z. What type of atom sits on that site, the occupancy of that atom, and its temperature factor at the end. So the temperature factor or atomic displacement parameter is something we might want to refine. So if I put an @ symbol in each of these lines, that tells TOPAS to refine an isotropic temperature factor for each of those sites. In terms of the fractional atomic coordinates, there are 4 coordinates that you can refine by symmetry in this structure. The x coordinate of yttrium can be refined. So if I put an @ symbol in front of that, it will tell TOPAS to refine that coordinate. And then the x, the y, and the z on oxygen 1 are also free to refine. So I'll give each of those an @ symbol. The scale factor here is set up to refine. It has an @ symbol in it. And then this line here describes the peak shape that we're using to describe the diffraction data. It's a pseudo-void peak. And I'm going to refine the U parameter, the V parameter, the W. I'm going to fix Z, refine Y, and I'll define X. So at that point, the file is basically set up perfectly to do a simple Rietveld refinement. Now, there are 2 important buttons to press. The first one is this TA with an arrow over the top. That's called the Save Set feature. If I click on that, what it will do is it will prompt us for a file name for the file that we're working with. By default, it gives it a sensible file name. It's the name of the data set. Word read has been appended, and then a code number, a serial number 01 has been appended. So I can accept that file name and click Save. Then if I come to this button here, this TA icon here will actually run TOPAS Academic. So if I click on that button, TOPAS will launch. It actually launches on my second screen. So let me drag that across. So this is the main TOPAS window that you'll see when you launch TOPAS. Normally, to perform a Rietveld refinement, we would click on this red arrow here and it would just run a refinement to convergence. Because this is a demo, let's click on this step button here. What happens when you click on the step button is the experimental data in blue is read in, and the first calculation of the model data shown in red here. If I zoom in, you can see that the observed data and the calculated data in blue and red respectively are very, very different. And that's because we haven't done any Rietveld refinement yet. If I zoom out on the data, you can see the R factor is 5,872%, so not a good Rietveld refinement yet. But if I click this red triangle here, that will run the refinement to convergence. And you can see on the little graph here, I start with a high R factor, and then as I do the refinement, the R factor comes down and down and down. And hopefully you can see on the screen here that the Rietveld refinement is now much better. The red data and the blue data look very similar to each other. I've got a question on the screen. Do I want to update my input file with the results of this refinement, which have been stored in an output file? It looks a good Rietveld refinement, so I'll click yes. Okay, because I started so far away from the correct minimum, I'll just do another round of least squares refinement to see what my final R factor is. And the R factor has come down slightly further. It's now 14.477%. And that looks like a good Rietveld refinement. What we can do at that point is minimize the TOPAS window and come back to jEdit. And what you'll see in jEdit is it's automatically reloaded the results of that refinement. So I can click on close here and come back and look at my jEdit window. And in jEdit, you can see that the R factor has been updated with the value that we've just observed. One thing to notice is that in jEdit, the quantities that we've refined, for example, the cell parameter, any number that's refining is colored in red. So it's very, very easy to see what's refining and what isn't. Numbers that aren't refining, like the cell angle alpha, is written in blue. Again, for the atomic coordinates, a refined coordinate is in red and a fixed one is in blue. So that's the basics of doing a very straightforward root belt refinement in Topaz using, as I say, these jEdit menus on the left. The working through these menus is sometimes the quickest way to work. It may be quicker actually to start with a file that you've already created. So you can always take a file that exists already and add to it. So for example, you might want to add an instruction into this root belt refinement to actually show you what the structure looks like at the end of the refinement. So you can add a Topaz command here. If I hit return and I type the command view_structure, that's the Topaz keyword for actually looking at the structure. Quite often you won't remember the syntax for these keywords exactly. It might be that you can remember the command is view something. It turns out in jEdit, if you type view and then hit Control B on the keyboard, you can complete the command. So what we want is view structure. And the nice thing is when the command is correct, it's colored in dark blue, so you know that you've got the syntax correct. If you can't remember the command at all, what you can always do is look in the Topaz menus. So we're using Topaz version 7. So if I expand the Topaz version 7 menus here, you can see there's a whole series of submenus. If I'm looking for a command to view the structure, it's probably going to be in this submenu here called phase level structure. If I expand that and I look through all of the possibilities, you can see the view structure option is here. So if I double click on that, it appears on in my input file. Now if I save this input file again, I don't need to relaunch Topaz because it's already launched. I can just switch back to Topaz, run that input file again, and this time when you do the refinement you can see the structure viewer. So there's a little structure viewer that lets you rotate around and look at your structure, view it in ball and stick mode, all the things that you'd normally want to do with to look at the results of your refinement. Okay, so as I say, you can modify an input file that exists already. Sometimes you might find it easiest to start with what's called a template file. Again, if I minimize these Topaz version 7 menus and I go to the Topaz Durham menus, there's a submenu here called templates, which has got some pre-set up files for some of the things you'll most commonly want to do. So let me shut this input file in Topaz so I've got a blank window again. And then let me come to the templates folder and I'm going to click on select template file. If I select template file, I've got a whole series of files pop up with some of the things that we commonly do with Topaz. So for example, a neutron root belt refinement, or at the bottom here, an X-ray root belt refinement. So if I double click on that, I'll get some text appear in my editor. What I can do now is file, save, and I'll save this as a file called temp.imp, and let me save it to the folder that I was working in previously, which is C have done this earlier, user data, DCH0, data, Topaz YouTube, demo 1. So let me save this file as temp.imp. Again, when you save the file as an input file, it automatically gets colored with the Topaz color coding. And the rules with one of these template files is wherever you see some text in purple with an arrow in front of it, you just need to change that text to set up the file ready for root belt refinement. So you need to give it the name of the data file. If I go back to my folder, the data that we were analyzing was this data set here. I'll copy that file name and I will put it on top of that purple text. So that's the file name that we should be analyzing. We need to tell Topaz the LP factor. So the LP factor here was actually 27.26. The type of radiation wasn't copper K alpha 2, it was copper K alpha 1. And then if we come down later in the file, there's some information about the structure that we need to enter. So what we can do is, let me get rid of these purple arrows. Let me get rid of this one line of bogus text here. So the structural information, we need to tell it the unit cell parameter. So this material had a cell parameter of about 10.6 angstroms. Let's type that in everywhere. Okay, the space group was actually IA bar 3. and then we need to type in the atomics site. So I could just type those in by hand, but just to save a bit of time, let me go back to the previous refinement sheet. Let me just take those sites, copy them from that file, and put them into this file. Okay, then hopefully this is everything set up to do a straightforward readvault refinement. Again, I can save this file and send it to TOPAS. If I come back to TOPAS, I press this little icon in the top left, it will delete all of the data that I was analyzing previously. So that gives me a blank window in TOPAS. You'll see here where my arrow is. TOPAS now knows it's to analyze the information or the instructions in this file temp.imp that we've just generated. And if I've got things correct, I should just be able to click on this red arrow here and do a readvault refinement. So that's my readvault refinement. You can see I've got a high R factor, 850%. That's because I forgot to do one thing in my input file. I forgot to tell it how many cycles of least squares I wanted to perform. So let's perform 100 cycles of least squares. Send this back to TOPAS again. Click on the run arrow, and hopefully that should give me a readvault refinement, which is more or less equivalent to the one we performed previously. Again, if I switch back to jEdit, that file has been reloaded. We can look at the results of the readvault refinement. So hopefully those two ways of working, either clicking through the menus in the TOPAS Darrow menus or editing a pre-written template file, will give you some idea of how to perform a straightforward readvault refinement in TOPAS. If you want more information about any of the things we've talked about in this video, you might find some of these resources useful. At the bottom are a couple of general resources on powder diffraction and readvault refinement, and at the top are some more TOPAS specific resources. You might find the TOPAS web tutorials useful, which are on my web pages. The link is at the bottom of the slide here, but if you just do a Google for TOPAS tutorials Durham, you should hit that site. There's also a link to the TOPAS wiki, which contains lots of information about TOPAS and how it works. And there's also a link to the TOPAS forum where you can ask questions about TOPAS, and hopefully one of the experts from around the world will answer those questions. I really recommend you read this document here. If you look in your main TOPAS directory, there's a file called technicalreference.pdf, and that's written by Alan Coelho, and it's got details of all the functionality of TOPAS and the mathematics of how TOPAS works. So you should really try and read that document. If you want something more general, you could try this textbook on the right called Readvault Refinement. It's written by Robert Dinnebeer, Andreas Leineweber and myself, and it contains the background theory of readvault refinement, and it also translates that theory into TOPAS syntax, so you can make the link between the theory and actually doing refinements in TOPAS. If you want something slightly more straightforward, you could try this article at the bottom in the Journal of Chemical Education. What we do in that article is again tell you the fundamentals of readvault refinement, but then we teach you how to do a readvault refinement in Excel. So you get to type in all of the equations that you need, and it teaches you how readvault refinement actually works. So hopefully some of those resources will be useful. Finally, I'd just like to thank a few people. I'd like to say thanks to Alan Coelho and to Arndt Kern. And then I'd like to thank my various students and collaborators over many years for all of the exciting challenges they brought in powder diffraction and readvault refinement. And finally, thanks to you for watching this video. And again, I hope it's been useful.